In this video, we will understand what is intrinsic semiconductor and effect of temperature on it, and the concept of electron and hole. As silicon is a semiconductor, so to understand intrinsic semiconductor, we will try to first understand what is intrinsic silicon. If you are given a crystal and we were told that it is a intrinsic silicon crystal, then it should be satisfying at least two things. One, that all the atoms in this silicon crystal should be just silicon, no other atoms. In the sense, no foreign atoms or impurities, nothing. It should be all silicon. And the second one is, as we are saying it's a crystal silicon, the atomic arrangement should be so systematic and periodic that there should not be any dislocations or imperfections. It should be a pure crystal. In fact, till now we have been seeing only intrinsic silicon since the starting of the course. So now let's use the band model and bond model that we have developed to represent this silicon crystal. So let me first use the band model, where we have this conduction band and valence band. We have defined that the bottom edge of conduction band is EC and top edge of valence band is EV, and the difference between these two values is called the forbidden energy gap. And the y direction is actually the electron energy, and the x direction is basically the distance. And this is the band model where the valence band was completely filled with electrons and we had no space or empty energy states available there. It's completely filled. Whereas conduction band is completely empty. There are no electrons at all. And this condition is true under the assumption that T is 0 Kelvin. And that's what we have been assuming since the starting. Now let us see the bond model, where we represent the three-dimensional crystalline structure in two-dimensional silicon atom model, which is silicon in the center and its neighbors, and each silicon was represented with 4 valence electrons for all of them. They have these covalent bonds where the neighboring atoms share their electrons. Where the center silicon has 4 valence electrons, it is sharing all the 4 with 4 neighbors, and each neighbor shares 1 electron to this center silicon. And if you see the other cases where this silicon, it shares with another 4, and even this with another 4, and this one as well, and this. So which means the whole crystal is being represented in this two-dimensional model, which we call the bond model, where it shows the covalent bonds. Now let me assume if we apply a potential difference across this silicon crystal at T equal to 0 Kelvin, there wouldn't be any electric current conduction through this material because there are no empty spaces in the valence band for the electrons to move, because the electrons are occupying all the states available, so no electron can basically move. And similarly, if you see the conduction band, there are all empty states and there are no electrons to actually move. So that's why we won't have a conduction of current through this material at T equal to 0 Kelvin. Let us see the same understanding from bond model, where these electrons that are present are all in the bonds and they are tightly held in the bonds. So when you apply a potential difference, these electrons are not going to be free to move. So as a result, you won't have any current flow in an intrinsic semiconductor. So here I'll say intrinsic semiconductor can also be called as a pure semiconductor. Similarly, intrinsic silicon is pure silicon, which means we can say at T equals to 0 Kelvin, the semiconductor acts as insulator, where it doesn't conduct any electric current. Now let us see what happens to this material as temperature is increased. Now let me take the band model where we have the conduction band, valence band, and the energy gap between them, Eg. Now as the temperature increases, the electrons in the valence band will find enough energy to actually go to the conduction band, which means let me assume there is an electron which is actually acquiring enough energy to go to conduction band. So when electron goes to conduction band, we'll have an empty space in the valence band. So when we have an empty space in valence band, you can imagine now if we apply a potential difference across the material, now valence band electrons can see a vacancy to which they can move, and you can see conduction of current. And similarly, the electrons that are present in the conduction band can see a lot of free empty spaces. They can actually move and give rise to electric current. Now let us understand the same phenomenon based on the bond model. So let me draw the entire bond structure here. Because of the temperature increase, the silicon atoms in the lattice, which are attached to the neighbors with the covalent bonds, will start vibrating. When the silicon atom starts vibrating, at a level, it might potentially break the bond. When it breaks the bond, what it means is the electron which is in the bond can break free and become a free electron, which means that this electron would be free, not in the bonds, it will be free to move, and it will leave an empty space here, which can be filled with any electron there, but this is empty space. Now, to have a correlation between these two models, bond and band models, this empty space here is actually the space that we have in the valence band, which is unfilled with the electron. And the electron in the conduction band is nothing but the free electron in bond model. Now, we're going to call this empty space in the valence band as a hole. This is a new term we are defining here. This empty space in valence band is called hole. The reason why we are defining this new term is, if you see, there are a lot of electrons. Let me just point here. There are a lot of electrons in the valence band. Now, when you apply potential difference, the electrons can move only if there is an empty space present, which will contribute to your conduction of electric current. If the empty space is not there, it doesn't matter how many electrons you have, they don't move, which means the conduction of current, because of the electrons moving in valence band, is dictated by the presence of empty space. So the presence of empty space is the important factor here. So the empty state in the valence band is called as hole. In other words, we can say it is vacant state in valence band. That's what we're calling it as a hole. It's a very important definition, and we will see more of it in a very detailed fashion when we discuss about conduction in semiconductors. Now, if we look at the conduction because of the presence of electrons in the conduction band, it's actually the electrons that contribute to the current flow. Now, you might say that there are a lot of empty or vacant states available in conduction band, but still we don't consider them because the current flow depends on the minority carriers in conduction band, and that is electrons. If you don't have electrons, how many ever states you have, the vacant states in conduction band doesn't matter. So that's why the number of electrons in conduction band, let me write this down here, number of electrons in conduction band will dictate how much current flows, and number of holes in valence band, of course, we'll say a number of vacant states, simply write vacant states in valence band dictate your current flow. So that's why we're defining a term called hole, which represents the vacant state in valence band, and electrons in conduction band is what is important for us, not the number of electrons in valence band. Now, in terms of the bond model, you can see here we have an electron which is free now, which can be under the influence of electric field if you apply the potential difference, and we have a hole here. Now, how does the current actually conduct with this hole? Now, this electron that you're seeing here can actually move to this point, okay, and then once it moves, basically you have a hole moving to this point, and the electron would be filling this point. So which means the hole is basically moving. And of course, we'll discuss this in detail when we go to conduction in semiconductors. But now the important point is we know what is hole, and the electrons that we are interested in is actually the number of electrons in conduction band, not the valence band. And one more thing, how do we measure this number of electrons in conduction band and number of electrons in valence band? In fact, this basically depends on how big is the semiconductor that you are considering. Let's say I take a very small semiconductor piece and a big semiconductor piece. Definitely, the number of atoms will be more in big semiconductor, so that you will have more electrons in this one and you will have less electrons in this one. So in that case, how do we generalize our theory throughout this course? So what we're going to do is, we won't measure the absolute number of electrons in conduction band or number of holes in valence band. Instead, we'll measure number of electrons in conduction band per centimeter cube. And similarly, the number of holes in, of course, holes are defined in valence band per centimeter cube. So this notation, we are calling it as N. N represents number of electrons in conduction band per centimeter cube, or else we can call electron density. And we're going to define P, which is the holes in valence band per centimeter cube. It's hole density. So that in case if you want to find how many electrons in this small piece of semiconductor and the big piece of semiconductor, you can simply multiply the dimensions of these with the N and P. Observing carefully, for intrinsic semiconductor, we know the number of electrons that went into conduction band would be equal to the number of vacant states available here. Because when we started, there were no empty states whatsoever in the valence band. How many ever electrons will go, those many empty states will be there. Which means in intrinsic semiconductor, number of electrons in conduction band should be equal to number of holes in valence band. So when these two numbers are equal for an intrinsic semiconductor, we're going to define a new term called N suffix I. This is called the intrinsic carrier concentration. This is a very important parameter because for a given semiconductor, let's say if it is silicon, at room temperature, this number is a fixed number. So this is a very important number that we will keep revisiting. Having said that, the point to remember here is N equals to P equals to Ni. Ni is a very important parameter.